So, welcome you everybody, and we will continue with lecture 2. After introduction lecture, we shift to lecture that will be related to description of radar signal processing. It is very huge task because, how you will see later, signal processing is radar is divided to many different parts before detection, sampling, integration, MTI filters, MTD filters, and so on and so on. Also about shaping of pulse, how we define transmission of pulse, and so on. So I think that this is maybe tough lecture from the whole series due to missing experience from radar, because usually, like in my study program, we have 3 semester and 3 different courses, and I need squeeze this 3 semester course to 1 lecture. So it will be tough, but I have a lot of picture, and during tutorial I must say I will share all this MATLAB codes, and it will be just visualization. Just forget about formulas, try just to understand principle, and if you have any question, of course we could discuss during break. It will be best one, because now I have about 80 of slides. So it will be a little tough out, but I think that we can handle it. So, always I will start with our central question: how do wind turbines interact with primary radar systems? To answer this question, we need solid understanding of classic radar. So we need to know how is measured estimated range, how target received, how radar receive echoes, how is measured angle, radial velocity, what is limits, what is performance, which power I need to transfer to detect some targets, because of course it is clear that if I need to detect some big plane, I don't need so big power because it is big target. If you want detect UAVs, you need some different type, and of course it is also related on distance, and there is about I will make joking 100 parameters of dependency of all these things. So I want on this lecture show you some really base thing that you will use it later on other lectures. So in case that you will not understand something, don't worry, then will be practical examples and more will be clear. So what is aims and learning outcomes? It is this. Now we start with description of basic architecture of primary radar systems. I will explain you how primary radar measures range, azimuth, elevation, and radial velocity. Also, I need to highlight what is resolution and ambiguity of measurement, because we could have, how you will see, ambiguity range and unambiguity range. So it is 2 different things. So it is also very important topic. Also, I will show you some videos of interpretation of basic radar displays. We call it ABC scope or PPI, we will see later. Then we need to understand how quantitatively we explain radar equation and RCS. RCS is radar cross section, and this describe you generally size of target in square meters. Then I will let you just brief information about about signal processing chain. So what is pulse compression? Because pulse compression is related to resolution of radar. if your resolution is 1 kilometers or resolution 30 meters, it is big difference. Of course, it is depends on then size targets. What is Doppler processing? Maybe you know what is Doppler frequency. Doppler frequency, from Doppler frequency, it is shifting in frequency, and from Doppler frequency we can recognize how fast, what is velocity of target. What is CFAR? It is constant false alarm rate. What is tracking? And so on and so on. So, we will start. So, basically transmission, and now we are on start. So imagine that we have radar and now it's transmitted our energy to target, to space, if there is some target or not. And this transmission of the signal could be continuous wave or pulse. And now if it will be continuous wave, we call it usually CV radars or FMCV radars. And I just want to inform you, we will not work with CV radars. Now I will focus from these slides only to pulse radar system. It is basically all primary radar system, majority of them working on pulse regime, something like this. So now I will, when I call about radars, it will be always in pulse system. So there is just some brief example. Imagine that is this our radar, and radar, this is coverage area. It could be 1 square meter, it could be big one, it could be 2D radar or 3D radar. It is depends if my results from detection is only range and azimuth, or azimuth, range and elevation. So our signals that is transferred from radar and spreading to area, of course not how to say, not only reflect energy from our target of interest, but from anything, from environment, from ponds, from woods, from mountains, even from clouds, how you see, from storm, I don't know, everything what is inside of area of interest, it will be reflected back. So you can imagine that what is included in the received signals? Reflection from everything. And now, in real time, you need to decide, okay, it is target, not target, it is reflection of environment. We call it reflection from environment, clutter. So it is what I don't want in my signal, because of course it could mask my targets. Because imagine that you have some small UAV, and this UAV flying like this, and this will be some metal solid wall. Forget about detection, because this metal solid wall will have so strong that reflection that will hidden your small target. So so first step, of course, in radar signal processing is detection. Then is from detection we will make measurement and processing of parameter. And what is base measurement and processing parameter? It is range, measurement based on transmitted signal. And how do you think that we measure range? When I transmit some pulse in specific time, then is reflected and travel back. We measure range based on delay of signal. How we can compute the delay? From cross correlation of transmitted signal and received signal. I get a delay, and if I have delay, then I know that speed is speed of light, and I can easily compute range. But it is so-called slant range, because you know range, but you don't know from which direction. Don't think that radar works in XYZ coordinates. It is only on polar coordinates. Of course, we could transform to XYZ, but you need more information how to do it. So it is range. Then is angle position based on directivity of antennas. If you will have 2D radar only, then measure only azimuth. So, okay, I know range and I know azimuth. So it is vector. Okay, there is clear information and relation where is target. If will be in 3D, then we have also elevation information. So generally you can have 2D or 3D radar. Okay, so we know position now of our target, but it is not enough. I know if target, what is speed of target or velocity. How I can do it? You know that my transmitted signal is in some carrier frequency. I don't know, 3 gigahertz, 5 gigahertz, 10 gigahertz. It is depends on frequency band when my radar operated. And if I will send, how to say, signal to my target, it will be target, that is movement, reflected signal will have slightly shifted frequency. Why? Due to Doppler shift, because it is moving. So it is clear if target is not moving, Doppler shift is 0, because it's not moving. If will be moving, there is some Doppler shift. And from Doppler shift, I can compute speed of target. So basically say, and I will take care only about monostatic system setup radar. So it is mean that I use only one antenna for transmitting and receiving, not bistatic, because in bistatic configuration is it in even more complicated, and it is not necessary for our case, because in ATC I don't think that exists any bistatic solution. I don't know this solution. So in ATC we use it only this monostatic solution. So I will continue. There is example I will show. I already show you in first lecture. Example of typical primary radar system. I put again because there is also system parameters. So this radar system from company L02 that I have suspicion is also in Guwahati, work in S-band. So it is bandwidth from 2007 gigahertz to 2009 gigahertz. So it is the working frequencies of this radar. It uses diversity transmission, short and long pulses, with power 14 kilowatts. So you think, oh, it is really big power. Why? Because this pulse is really short. It will be some microseconds, it will be some 200 nanoseconds or something like this. So it is big power peak, yes. So also this radar has azimuth coverage 360 degree. How is possible? Rotation of antenna. Elevation coverage up to 40 degrees, so it is mean also make this movement, but only to 40 degrees. Why? Because usually you want to detect all target that incoming to your side, but not from up. So it is like typical parameter. And range depending on configuration. It could be like their range. What is detectability of target is like 80 kilometers, and range of course depends on size of target. You can't say, okay, my radar could detect target at 80 kilometers. It is not true, because imagine Airbus for 500 people, okay, you can detect it from 80 kilometers. And small UAV, I doubt that you will saw this small UAV from 80 kilometers. So it is not true. So range depends on configuration, and usually see there more parameters. So this information is that, okay, I can detect target up to 80 kilometers that have radar cross section 2 meters square with probability, and be careful, there is also probability of 80%. Of course, if you want to detect UAV, it is not for detection of this small target, but like example, I can detect UAV up to 5 kilometer with RCS up to 0.1 with probability 90%. So range is always also how you can see variable, because it depends on size of targets and on probability. You want higher probability, range will be lower, of course, because you need to be more sure that this target. Because still remember, we get reflection from anything. So any surface that influence your received signal, and then of course it could be hidden, it could be mass, and so on. What is antenna parameters? Antenna gain 44 dB, decibels. It is dual beam antenna. You can see that there is one beam and a second beam. It is for long and short ranges. So this radar switching, like there is some special modes, and always check long distance, check short distance, long distance, short distance, or different parameters. Of course, I don't know, it is programmable, so you can change it some of these things in parameters. Or you can switch to mode that, okay, I am interested only in long range, I am interested only in short range, and so on. And this radar has two long and short pulse. Also, this is polarizer for suppression of rain reflection. It is very important because you will be surprised how weather can influence range of radar. Because if it will be really big storm or snowing or something like this, your range from 80 kilometers will lower to 20, 30 kilometers, because reflection of snow it could be really high. So if somebody told you, okay, we have perfect radar up to 100 kilometers and don't provide any other information, start be suspicious. There is second example of weather radar. I put it because it is typical for primary radar system also. It could be 2D, 3D. It is a very well known company, Vaisala. I think that is from Sweden or some north part. I think that's Sweden country. It works on C-band, so you can see frequency is from 5 up to 5.7 gigahertz. Why use different frequency? Because this frequency is suitable for measuring of like atmospheric artifacts. It is better. If you will go to higher frequency, then mean that wavelength will be shorter, and you get reflection from like smaller objects, and then your signal don't pass through like snowing or something like this. Coverage is about 300 kilometers, so it is big coverage. Range resolution is 75 up to 300 meters. And again, you can see depends on length of pulse, long, short. So it is one of parameters which we discuss later, and it is very important. Azimuth coverage 360, of course it is weather radar, so we are interested around all of us. Azimuthal elevation resolution is about lower than 1 degree. Okay, and distance. Resolution depends on distance. Up to 50 kilometers is about 1 kilometer. Distance at 100 kilometers is a resolution almost 2 kilometers, and distance 250 is 4 kilometers. Why? Because resolution cell, if you can imagine, it is one cell, classic cell. it is not constant everywhere, because if you are far, it is go to wilderness. So it is clear that if you will be increase range, the resolution, how to say, decrease, because resolution cell is bigger. And Doppler resolution depends on PRF. It is pulse repetition frequency, you will see later, is plus minus 16 up to plus minus 64 meters per second. Why we need Doppler resolution in this range? Speed of wind. Of course, if you will have some low speed wind, high speed wind, because if you check weather forecast, always they saw also what will be speed of wind. It is from this type of radar. Okay, you already saw examples of that different type of radars, generally different type of any kind of RF service works in different bands. And we need to discuss what is spectrum allocation and utilization, because spectrum allocation we need strictly follow. Why? Imagine that we have DVB-T and you are watching on your favorite TV series, and now somebody use transmitter on same frequency, exactly same like is DVB-T. What do you think that happens? He will start sending some signal. It is not important which one. And what will happen with signal of DVB-T? It will be sum of both signals. But if I will make summation, I will change amplitude, I will change phase, and what's happened? My television don't understand these signals, because it is not DVB-T signals. It is DVB-T signals plus some other signal. So it can't follow format of DVB-T, and what's happened? Nothing. You don't see any screen. And it is same as like if somebody use GSM, what's happened? GSM stop working, because somebody stole your frequency band and start transmit on frequency your band. And again, summation of both signals makes that my phone don't understand this receiving signal, because it not will be GSM signal, it will be GSM plus something, and we can call it noise, and stop working. So now I think that it's really clear that we need follow strictly rules where I can transmit. And imagine what it mean for us. Now you want to discover some influence of wind turbines. You can't just make design measurement chain and go to place and start transmitting. You need permission. Without permission, if somebody catch you, oh, it will be really, really big fine, because you stole somebody frequency that pay for this frequency. So you need to be really careful about this. Okay, so signals we could divide it to two base category: band limited signals and UAB. ULB is mean ultra wide band signals, and it is really high, huge bandwidth. I will not care about this type of signals. We will take care about band limited signals. And this is example of frequency allocation table. It is from 3 kilohertz up to 300 gigahertz, and each area means some, how to say, reservation for some service, but not for individual service. But this is like radio navigation, this is for broadcasting, this is for also broadcasting, there is for FM radios, AM radios, DVB-T, and so on and so, radar, sonar, I don't know, for like example for some mobile communication is there, and it is clear if like your GSM operator have some part from this bandwidth, then it is reserved for him and he pay big money for reservation. So if somebody just start transmitting on same bandwidth, whole GSM network stop working, and what's happened? Some special authorities will try trace you who transmitting illegally, and you will definitely go to jail, or fine will be so big that you will be surprised, because they pay big money for this reservation. So of course they are very careful about this. Okay, frequency allocation and utilization is, how to say, managed on World Radio Communication conferences, and they decide, okay, in this frequency band we will use for radars or for radio navigation, this frequency band we use for something else, some other services, and it is worldwide. But of course that then is divided to some small part. Then we have national agencies, because for me it's not important if in your country somebody transmitting GSM signal in some frequency. Of course in Czech I can use it, this frequency band. Why? Because we are so many thousand kilometers far away that it is not important. So then each country like operate with this frequency, handle with this frequency independently. But it is like global point of view, country point of view, and then even in your case like state point of view, because of course if country Tamil Nadu they use it some frequency, in Assam it's not important, it is also long distance, so why not, they can use it. But you understand this mechanism, this control mechanism. I think that this is enough, and I will show you frequency band of radars. Radar system generally are grouped into commonly used bands, and there you can see which band use radar. Usually we use L band, S band, C band, X band and KU band. I will take care mostly now about C band and X band. C band, it is about C band, it's from 2 up to 4 gigahertz. It is for precision landing radars. Then C band from 4 up to 8, and very important is for us X band from 8 to 12 gigahertz. So this frequency is mainly used by radars. Then we have automotive radars, and what you need for automotive radars? Really huge resolution, because you want to detect pedestrian, children, I don't know, dogs, anything, something really small. So it is clear that if I want increasing resolution, I need increasing frequency. So, and for this reason, automotive, it is in bands about 40 up to 70 gigahertz, about 75 gigahertz, I think it is automotive industry radars, because they have big resolution. But what is mean for range? Very short range. It will be up to 200, 300, 400 meters only, because anything, it is depends on wavelengths, and wavelengths depends on frequency, of course. So it is clear, how to say, relationship between this one. So I will try check. Okay, meteor radars, it is in KU, it is from 12 up to 18 gigahertz. Then we have battlefield radars, police radars, and so on and so on. But I think just remember, for us is important L, S and X band. This three is very important from point of view radars. There I make repetition of these slides because I want to give you now more information on this. So this is typical blockchain of monostatic radars, where TX means transmitting site, which include waveform generator. Later you will see what is waveform generator. Generally, how looks pulse? It is just amplitude modulated wave. It is just rectangular. It uses some special kind of modulation, and so on and so on. I think that until present days could exist 50 different kind of modulation, or combination is almost unlimited. So it is depends what you want to detect, which resolution you need, what is, how to say, what is, of course, you know that military radars you very often want are resistant against jamming. Why? Because they use special type of modulation that is resistant to this kind of jamming. For civil, we don't use this special kind because we don't need it. So it is waveform generator. This, after we generate waveform in TX, that includes pulse shape, carrier frequency, modulation, if it's LFM, so linear frequency modulated, non-linear frequency modulated, or coded modulated. Maybe you know Barker coding, and some other type of coding. I will show you also later. So then waveform from baseband is modulated to your to carrier frequency, because of course we are transmitting on carrier frequency, and then is fed to the transmitter. Transmitter is typically high power amplifier, because you need big power, because you want to illuminate big area, and you know that like your power decreasing with R squared. So it is mean your power increasing very rapidly, quickly to 0. But you want to detect, remember, target up to 80, like example, kilometers. So 1 divided 80 kilometers square, it is really big attenuation. And imagine that we have like long range radars up to 500 kilometers. Is it clear that these radars will have low resolution because they need work on much lower frequencies, because the attenuation will not be so bad. So again, this is first relation. Then from transmitter TX we go to duplexer or circulator. I already described. It is protection of receiver, because when I transmitting my high power pulse, this is unconnected, this part, because if this high power goes to receiver, it will be completely destroyed. Why? Because receiver handling with receiving signals, and when it will be 1 billion times slower in amplitude than my transmitting power. Almost it is hidden, information about targets is almost hidden in noise. So this must be really, really big sensitivity. So of course when I transmitting, I disconnect it. When I listening, receiving, I connected this part and disconnected this part. So it is still switching in pulse shape, how we will see later. Then we go to ADC. Usually, of course, in receiver and in receiver side, first what we need to do is amplifying of my signal, because it is so low that I can recognize anything in this type of signal. So I need really good amplifier, analog of course, with really low noise number, because I want the lowest influence of my received signal. Of course, and if my amplifier will be low quality with some noise, then will influence my signal and I lost all information about target. So, but it is maybe your area, because I am more signal processing guy, not analog processing guy, so it is more for analog processing people. Then there is some filtration, because your receiving signal has some bandwidth, and I of course make limitation to bandwidth of interest. So there is some few things, but not important for out. It is important for designer of radars. Then we go to ADC converter, and there is clear message. There we stop analog domain and start digital domain. And IQ, it is mean IQ samples of my signal. So I make sampling. Of course, I need full thing, sample theorem, and all this thing that you know for sure from your studies. It is very well known. And I produce complex sample, I and Q sample. Why I don't work only with amplitude, but I work with amplitude and phase? Reason is clear. If I have only amplitude, I have information only about distance, because it is time delay. But if I have phase is frequency, and frequency is speed, and speed is velocity of target. So I need both, of course. If you are interested only in range, okay, just work with amplitude, it will be simplified. But generally, you want information about your target, especially if will be some enemy, you want to know how quickly speed up to your side. Then we go to signal processor. Signal processors make a lot of function. I can call it pulse compression, Doppler processing. It is include MTI and MTD filters, the moving target detector and moving target indicator. Generally, what is mean? MTI filter just removes everything from your signal what is not moving. So the reflection of environment. I don't want this information in my signal, because I am interested about target. And what is MTD? Moving target detector. And imagine MTD, it is bank of filters. So it is like parallelly you have 5-10 filters. And first filter detect targets that have speed from all like 10 km per hour to 20. Second filter from 20 to 40, from 40 to 60. You get my point. And you like to input to bank of filter is placed your IQ data, and of course only through some filter will pass, because other filters will attenuate, because every filter is designed for specific speed range. Like example, like this one. Then our pre-processed signals, we call it like primary processing, go to data processor. And there, why I divided signal processor and data processor? Because signal processor, we are working with samples. It is signal samples. But after this, we work only with data. And what is mean data? It is detection in this range, or it is not detection. It could be easily in this range, cell range of my radar is target 1. It is no target 0. It is data. It is different type, but it is data. It is not anymore signal. Then in data processor also we build plot, tracks, and so on and so on. Because we are not only interested where is target, but what is kinematics of target, how he moving quickly, he speed up, slow down, where he go. So of course you need to follow your individual detection. And around this system we have built-in test equipment. It is for checking health of your radar system, if I can say easily. And power supplies, of course, power supplies, you need electricity. And antenna gear, it is for a rotation. So, and last one is communication, and it is communication interfaces, because your radar usually don't work standalone, but it is connected to some higher system, because of course you will send information from individual radar to some headquarters for fusion of data, because they need information about the whole picture, about the whole situation. So it is something like this. So is it clear? Can I continue? Thank you. And now we pass through individual things about measurement of position, slant range, and so on and so on. So imagine we are not work on Cartesian coordinates system, but we are working on spherical, always. So you need to think how also convert this information to Cartesian, because what I want to see, I want to see map and where is target. But it is not so easy. Imagine that you have two independent radar and each one work in spherical coordinates. But these two spherical coordinates, imagine that is 1 and 2nd radar, and there is target. For this target, it could be 12 kilometers, for this target 5 kilometers. How you can connect together? It is same target, and you get two different range. Of course, you are working in two different spherical systems. So fusion, it is really complicated thing. It is not easy, because for one radar it is one radial speed. For second radar it is different speed and different range. It is completely different independent value, and it is produced by one target. And now imagine you have situation around Delhi airport where will be, of course it is secondary, so they have information from ADS-B, but if stop working they need use information about primary radar. And now imagine situation in your area of interest, if it is 50 targets and you are completely lost almost, and you have 3 radars, and you need to make combination of 50 targets and always found 3 measurements from individual radars and how to interconnect it together that correspond only to this single target. It is a lot of combination. 3 up to 50, and you need, and only 50 of them is correct, rest is mistake. So it is also very interesting task, but it is more for mathematician, because this optimization is really hard. Okay, so I will continue. This is azimuth phi, and this will be elevation in 3D, and this we call it slant range, and this is x, y, and z. There I just show you brief formula how you could recompute from Cartesian to polar coordinates to spherical coordinates. So also is slant range, we call it R. It is clear that azimuth range is from 0 to 360, because you can see circle, it is clear. And elevation is angle over equatorial plane, it is from 0 to 90 degree. So I think that is clear. What we all, if our target is in move, then we measure also Doppler frequency, and based on Doppler frequency we measure radial velocity, not like classic velocity when you are driving car. It is radial velocity. Be careful. It is not the same. Okay, and now what will be interesting for us is, and what is precision, what is ambiguity, how you will see, and what is resolution capability of our radar target position measurement. So, can I continue? Clear? Thank you. Sorry, I always ask for confirmation because it is much better if you have question I can answer if I know answer. So about range measurement accuracy. So how I say, we have slant range measurement. Slant range measurement is based on a received signal delay measurement. So it is called matched filter output, and I will later call it also mismatch filter output. But now matched. What is matched filter? It is filter that give you best, how to say, best results for signal to noise ratio, and it is based on cross correlation. So what is mean generally? I take my transmitted pulse in specific time, I waiting for received signals, and I might make cross correlation of both signals, and of course somewhere will be maximum. It is like example, if you have rectangular pulse, just pure rectangular pulse, and make cross correlation, you will get triangle. Is it clear? Because you start moving and it is increase. When it's just this, it is this maximum and just disappearing. So cross correlation told me what is mutual area, how to say, and my maximum is in some specific time, and it is my time delay that I need to find. This is example of a cross correlation of matched filter without compression, so it is just rectangular pulse. If we will make some compression of filter, I will later show you what is it. Oh, no, it is after compression. Sorry, it is without compression, and this is after compression. So this is just cross correlation of rectangular pulse. Sorry, I made mistake. And this is spectrum of pulse. And you know probably from Fourier transform that is since function sine x divided x. So since you call since, yeah. This is main lobe. Usually we need 3 dB main lobe width, and this is side lobe. Of course, what we want, that energy of this is same like energy included in this, but what you need for best resolution of based on best resolution and minimal error in accuracy, what do you need? It will be this slimmer and slimmer and slimmer, it will be better. Why? Because imagine you have two targets that is 200 meters far away each other. It could be hidden that it will be like interconnected, just two sines x function, and it will be one wild main lobe, and you think it is one target. No, it is two, but you don't have enough resolution. So for me will be best if will be this zero, and wall energy in will be in one very narrow peak. It is mean better, higher resolution, I can recognize two targets, and it is based on this. So it is main lobe, side lobe, and now how we compute this time delay. Time delay is of course 2r divided c speed of light y2, because one way and second way, so it is clear. So Slant range is computed like my delay multiplied with C divided 2. Easy. What is range measurement resolution or accuracy? It is approximate formula. It is not exactly like this one. It is delta TD. It is differences between two like samples, targets, exactly. It is 2dr. It is resolution in range divided C, and I could convert it to this one. Okay, if I will use after compression and only rectangular pulse without any inner modulation, then this time delay is could be evaluated like plus minus 1 divided B. So what is B? It is bandwidth of main lobe. So range resolution depends only on one thing: bandwidth of your pulse. Only on bandwidth, not, and be careful, not on length of bandwidth, only on bandwidth. So it is clear I need more and more bandwidth to get slimmer and slimmer, or higher and higher resolution, it is better say. Okay, I will.
Side lobe ratio, what information will give?
Yeah. Okay. It is about energy, because you want all energy that will be in your main lobe. Why? Because detection you provided by this main lobe, and side lobe ratio, it is ratio between amplitude main lobe and the lowest and the highest side lobe. So it is mean that you want this ratio to be so highest, because then it is mean what? If this will be like only this one or this one or this one, it is mean more and more energy in main lobe and low energy in side lobe. So this ratio you want to be to highest. And why? Because imagine that also there will be some noise. This is without, of course, noise. It will be nice, something like this. And if this ratio will be low, then the main peak could be hidden also in noise. So generally you want this ratio to be biggest. And for this reason, unmodulated rectangular pulse is not suitable for radar, and we always use some modulation, because this ratio is about 13.5 dB only. But if you will use some modulation, some special kind of modulation, could be up to 40, 50 dB, even exists some about 60 dB. So it is about this one.
Increase the resolution of the
Not resolution, but it tell you more energy in main lobe, and you want more.
Wide iteration.
Sorry?
To have wide iteration.
Yeah. Exactly. Okay, there is situation about resolution, or from accuracy to range resolution. There you can see that we are transmitting this, and we have two targets in similar position. You can see similar range. You can see that is slant range. It is like on circle. So it is not depend if this will be, I don't know, there. It is still same slant range. And resolution, this is very close target, distance R1 and R2, and this is my resolution. And what will be? result after matched filtration, I will get something like this. I can still recognize. But if this will be lower, you will see one big main lobe, one target, or two targets. So I think that message is clear from this one. And imagine that you have more and more targets. It could be more and more complicated to get all this information. Yes. So again, be careful, resolution is set by bandwidth of target. Why bandwidth? Because it is this one. If will be generally bandwidth higher, resolution will be lower. Can I continue? And now range ambiguity and its resolution. I honestly must say that I have little worries about this part because it is not much easy. And I will try to explain. Imagine we are in time 0 and I just forget about this one now, for now, and I transmit pulse. It will cost 1 microsecond, I don't know, some period of some time. And what I doing now during this time, waiting for response, for response about target. Is this target, not target? And I get this response. Just forget about this one. Okay. But I am not sending one pulse. I will send pulse every half second, every it is not true. Every, I don't know, 100 milliseconds pulse. And now imagine, I will send this one and get this one. I will send, after this time, I will send this one and receive. This target is stable, don't moving, and it is still same position. And get this one. I will send this one and this one. So it is transmitted pulse. And now, how you want compute range? You will tell me, yeah, this is this time delay, and I will compute range. How you can be sure that this answer is from this pulse and not this pulse?
Yes.
It could be close target or this target. And this is ambiguity. And this is, you get my point. It is not easy. Imagine, you are sending pulses and getting responses, but you need to be sure what is ambiguity range. And after you will be in higher, like in outside of this ambiguity range, you will receive better response. So imagine, my target is 60 kilometers. Of course, this is time delay, but I will recompute to range. But I can identify this target like target that is 5 kilometers far away from me. And you will be surprised. No, he's 60 kilometers. But my radar told me it is 5 kilometers. And it is wrong. So it is clear. I think that this is clear. There I need to be extremely careful because I can't listen for answer very long time. Only to some maximal time delay. Why? Because then I start transferring transmission of new pulse. If you get my point. And then again. In tutorial I will show you this one about ambiguity range, how to compute, how to deal it. And is it clear? Can I continue? It is clear why this is ambiguous target because I don't know if it's this or this. So imagine 60 kilometers, 5 kilometers, but true range is 5 kilometers. Measured range is 60 kilometers, but measured is 5 kilometers, but real is 60 kilometers, like this example. And how you can avoid it about this? This space between transmission of individual pulse every 100 milliseconds, like example, we call it pulse repetition interval. You will saw it maybe 1000 times in my presentation. I will call it PRI, pulse repetition interval. And inverse value of pulse repetition interval is pulse repetition frequency, PRF, because sometimes it's for us suitable work with PRI and sometimes with PRF, but it is just inverse function. So how we can avoid this ambiguity? I will make higher interval between transmission pulses. Is it right? Yes. If I will wait longer time before I transfer second, like example, this knot will be there, but I will send this and then this, then will be okay. It is unambiguity. It is okay. It will be clear message where is target. But I tell you that is not possible. And you know why? If I will do it, I will get higher unambiguity range. It is true. But due to this, I will completely destroy resolution in Doppler. So you need to choose. You want good unambiguity range, then you will get really bad resolution in Doppler, so you can't recognize speed of targets. So it is leveraging. You need to be really careful about this one. And remember short long pulse about that I show you in real radar. It is about these ambiguities. So we use different regime, different these things because we can handle it. So it is about this one. So okay, I can improve. Higher PRI. Doppler will be destroyed, how you will see later. Because Doppler is computed from individual pulses. I will show you. There exists one tool how we can handle it, and it is called staggered PRI. What this mean? It is our classic situation where is non-staggered PRI, fixed spacing between samples, everything is clear like on last slide. But ambiguity target. But if I will use staggered PRI, and what is mean this? That I transmit like staggered PRI, that I transmit pulses, but not always in the same time. Imagine, first I will send in some time, and then not constant constant gap between two pulses, but second pulse will be slightly shifted, time shifted. So what is mean for me? From first pulse I get ambiguity range, from second I also get ambiguity range. So I have two wrong ranges. Why help me? Because by comparison of these two results, I can find solution and exact value where is my target. And it is called staggering PRI, staggered PRI. So there is some slight shift. Imagine it will be 1 millisecond and 1.1 milliseconds. Well, it is like jittering in pulse. It will be, of course, in specific times values. It is not random, but it is like, it will be like moving like in time.
We received the number of samples is more than at that time, and we have compared compare the both and after?
You compare like both results from time delay. So you have like in my example you will see that you have like one ambiguity real target will be in 210 kilometers, but my detection of this will be on 60 kilometers, and always you will receive 60, 60, 60, 60, 60. But it is wrong value. But from this case, with staggered, you will, from first pulse, you will receive, I don't know, 150, and from second, slightly shifted, 120 kilometers. So I have two bad values, but due to one equation I will show you later, we can solve this problem, and result will be okay, my target is 60 kilometers far away, or I don't know, some value that is correct. So it is so-called staggering, and very, very often is used almost in all primary radar systems. And why I talk about this when we talk about wind turbines? It will be close. For me, it's two targets, and it could happen that will be masked. It's the same problem, because what is reflection from wind turbines? It is target. And how we call it, you have two different type of targets. Target of interest, that I care, and target of non-interest. And what is non-interest? Everything what is not interest. It is easy, just opposite. So, and I must say, target of non-interest is definitely wind turbines. It is clear. There is little advantage, because if you place a target to some environment, of course, what is advantage of wind turbines? They are not moving. I mean, change position, they are static. Unfortunately, they have blades. And this causes our problem, because if will be only tower that is not moving, I will just use MTI filter, moving target indicator, and just remove it, this clutter away. And if will this happen, I will not have lecture on IIT, because it will be easy solution. But of course, this blade causes Doppler shift that is really in similar values like Doppler shift of my targets. Because you will be maybe surprised, but if you have blade about 80, 90 meters and rotation speed, I don't know, 9, 10 RPM, then on the tip and the end of blade is rotation speed about 800-900 kilometers. And it is speed of my civil of my civil plane. Okay, can I continue? And now I will show how to solve this, but just it is easy, don't worry. And I also all program on my MATLAB, so you can just easily use the script. So true time delay of target is true, tau true is 2 multiplied with this slant range divided C. Unambiguous range depends on pulse repetition interval. So it is C multiplied by PRI divided 2. It is clear, because it is length of this interval divided 2. It is maximal unambiguity range. But if my target will be far, I am outside of this unambiguity range, and we have problem. We need use to stagger. But my measurement is tau true modulo PRI. Why? Because everything is shifted to my PRI, like alias Z, if you understand me, always to base interval. So for this reason, imagine if this correspond time delay, true time delay 200 kilometers far away targets, but my PRI, my unambiguous range is defined by PRI, is shorter, then this time delay, my radar C modulo PRI by some value. So result, measured time delay will be much lower. And what is mean? Okay, I will see target that is in slant range that is closer to me, but it is not true. So it is just modulo PRI always. Delay to range, okay, if I will recompute this one, and of course I will work with slant range, it is again, it is what I measure, what is true, modulo unambiguous range. It is still same, but it is just conversion from time delay to slant range, but it is, you can see it is same. So how to recover? I just put this formula later during tutorial, you will see more in detail because it is not necessary. We need solve this equation. We need find N1 and N2 to be correspond this equation, and if we will found it, result is true range. And later I will show you with exact values and we will compute, you can test it. So, is it clear this one? I don't know how we can handle it. We are on slide 14 from 80. Okay, I will try speed up. Azimuth measurement. Generally, azimuth measurement works in a way that is really quite similar to range. But now for us is antenna angle where you are looking. And what is depends resolution, of course, on my antenna pattern. Be careful, it is this not spectrum, it is antenna pattern. So where is radiation, maximal radiation of my power is in main beam. And we are take care always not about this maximal value, but minus 3 dB. So this is definition of my resolution in azimuth. And again, what you want? Slimmest narrow, thank you. Narrow will be better because I can easily recognize. And this we don't want. We want 0, but it is not possible physically. It is theoretical only. And this causes us, this cyclopes of antenna causes very big problem. Why? Because I can detect target by this. But this is different. It is angle. So I get wrong azimuth. So we are not take care about maximum. Why? Because maximum can slightly movement. It is depends on many things. So we care and 3 dB width of main lobe. I think that I will continue. And there is just a list of azimuth measurement influence. What everything could like make me problem with in azimuth measurement. It is pole to pulse fluctuation. What is mean? You transmitting pulse in specific times. But this is not true because there is some oscillation of pulse to pulse because you never have absolute value. Frequency agility, because you use like carrier frequency 10 gigahertz. No, your oscillator is not so stable. It not will be always 10 gigahertz. It will be plus minus some hertz. But again, it is wrong. It causes your problem. So pulse to pulse fluctuation impact on azimuth is jitter of detected maximum, because I don't know where is exactly maximum of antenna beam. And for this reason, I don't care about maximum 3 dB beam width. Frequency agility. So again, carrier frequency is jitter. It is biased or jitter due to spectral RCS variation. Again, jittering. It will be, you don't get exact value. Also, I am sending pulse with some amplitude. Amplitude is not stable. it is not constant. Again, it will be some jittering, something like this, because I can't make so high, like infinite stability, of course. And it will be some random or systematic offset, and then flag maxima, low slope, it will be high sensitivity, a large error, but it is not important. So it is this 4 azimuth measurement influences. Okay, what about height and elevation measurement? Height and elevation measurement, it is not easy with single beam antenna, but this is based usually in 3D radar with multiple beam antennas. What this means? That I have no one beam that transmitting, but multi-beam. And from comparison of the results, like imagine, one beam is this, one beam is this, next this. So I get like measurement from different beams, and then of course I can evaluate elevation. Multiple beams properties, higher gain, easy installation of multiple transmitters, lower sensitivity to meteor clutter, low precision. What about height? Or height? How is your pronunciation? Height? Height. Sorry. I am not native. Height. Usually we use it some barometric height measurement readout from SSR. What is SSR? Secondary surveillance radar. It is radar that is, it is devices that is placed on plane, or we can use GPS information about height, ADS-B, and so on and so on. So it is height and elevation measurement is based on this one. It is important, especially of course for air traffic control. So, what about radial velocity measurement? How I say radial velocity measurement is based on Doppler shift. There is interesting graph that told you all this information. Imagine, on axis X we have PRF, pulse repetition frequency. It is inverse value of pulse repetition interval. So, if will be pulse repetition interval longer, it will be shorter frequency, of course. And I have a higher unambiguity range because it is longer period. But it is good. So you can see it is this curve. So for 1 kilohertz, it is mean 1 milliseconds, 2, 3, 4, 5, up to 10 milliseconds. I have unambiguity range 150 kilometer. So everything under 150 kilometer I perfectly detect like slant range. Good. But what's about radial velocity? Unambiguous, because it is so same. It is same principle. Lower PRF, lower unambiguity range. So it is against, it is just opposite. It is bad. And what this mean in reality? Imagine velocity based on measurement of Doppler shift. If I will have carrier frequency like 5 gigahertz and 10 gigahertz for comparison. If I have 5 gigahertz, then it's clear that due to motion of my target, my velocity caused some Doppler shift. And if will be lower, this PRF, because it is connected with this PRF, if will be lower value, then this, how to say, velocity of target caused lower Doppler shift. But if will be lower Doppler shift, resolution of this velocity will be bad. So for higher frequencies will be better. So from point of view radial velocities, resolution and detection, I want highest PRF is better. But if I will use 10 kilohertz PRF, my unambiguity range will be 12 kilometers. If I will use 1 kilometer, 1 PRF, unambiguity range will be 150, but on 10 gigahertz I even can't recognize it is under zero, because I can't recognize of movement of target. So it is like two things that go against each other. And again, you need to make some leveraging, something like this, of course. And it is really not easy task. And so this is clear. This is on this axis Y. It is slant range, maximum unambiguous, ambiguous range, that decreasing with PRF. And on opposite, there is speed of targets. And radial velocity ambiguous is definite for always. Of course, it is independent on carrier frequency. For each carrier frequency, of course, you have different lambda, different wavelength, and it is correspond to different line. So there is unambiguous, yes, there is no. So it is like you have two axes Y. It is a little confusing graph, but I think the message is clear. If you want this good, this will be bad. If you want this good, this will be bad. So you need to be somewhere in this area, of course. Where? No, Doppler. No. You transmit. You are transmitting pulse. It is just some modulation in some frequency, carrier frequency, but Doppler is only on receiver side, because imagine if you are transmitting something, there is no Doppler. It is just high frequency pulse. But this high frequency pulse in 10 gigahertz just hit target, and due to this hit target, due to movement of target, this carrier frequency will be shifted by Doppler shift. So it not will be 10 gigahertz, will be 9.9 gigahertz. And from 100 kilohertz difference, I can compute speed of target. Oh, sorry. I can compute speed of target. And this tell me what is maximal speed that I can detect. So it is like this connection. Again, there is radial velocity measurement if I have low PRF, high PRF, or medium PRF. So low PRF, unambiguous range is large, good. Doppler velocity ambiguous, low. Good for long range surveillance, poor velocity measurement. Vice versa, high PRF, it will be completely. So we are operating in medium PRF. And unfortunately, both partially ambiguous, because you need to be careful. And honestly, this is not easy task, and a lot of radar engineers leveraging what is better. And of course, also depends on purpose of this radar system. What is more important for you? What is more important for your client, customers? Okay.
Depends your output.
Yeah, what you want. Yeah, exactly. But this is used in practice. And ambiguities, even for range and for velocity, is based in signal processing, and you just remove it by solving this one equation.
So what if we use a separate transmitter and receiver, and their ambiguity will be removed and all things? Like separate transmitter for
Yeah, it will be bistatic.
then this problem.
I don't have board there, but bistatic combination is always triangle. Imagine transmitter, receiver, target, and now you are in big trouble, and I will show you. Transmit, reflect, and imagine you measure bistatic range. It is not slant range, and where is location of target? It will be ellipse. And where is located in ellipse? You don't know, because it is this plus this is one value. It is what you are measuring. It is this range, but it is ellipse, and results will be still same. So you need to have minimally 3 transmitters of opportunity, and from cross sections of all ellipse you will define where is target. But can you imagine how many cross section will be there from 3 ellipse for one target? 2, 4, 6. Okay, one target. And if you have 50, it is billions of combination, and you need to solve. Okay, which is right one? I make PhD on this. It is not easy task. It is really billion of combination. So stay in monostatic. No, I joking, but in bistatic is not using like in air traffic control. Or if exists, I don't know it honestly. I never saw it.
Sir, why don't you typically combine I have always seen that in time of arrival or any method we mostly use the range measurements, but very often we avoid the angle measurements. Angle measurement is also there, right?
Yeah, yeah.
But we
It is this azimuth.
If I have bistatic range, angle and azimuth, I can specifically say where it is on the ellipse. No?
Because we know that the distance between the transmitter and
But you, yes, but it is only one combination receiver and transmitter. But then you have same transmitter and other receiver. Same receiver and another transmitter. It is completely independent. So all combination is completely independent in bistatic solution. During break I can just draw you picture that is not so easy, because always you get triangles. Transmit, like receiver, transmitter 1 and target, triangle. Then you have one receiver but another transmitter, and it will be another ellipse. So another bistatic range and another bistatic range, another bistatic range that correspond to one target but 3 different values. And now imagine you have more targets. How you can know that this 3 range correspond to this one target? You don't know. How you can choose it? You don't know. It is completely independent. So you need to compute all combinations. Believe me, or I can send you some more information about this bistatic measurement, but in bistatic generally it's more and more complicated about this one. It is not so easy. Okay, and about ambiguity of radial velocity, this is visualization of blind speed. You know that in range we have ambiguity range, unambiguity range. Unambiguity, it is range that I can perfectly detect what is range of my target. After this is ambiguity range, because I can't be sure, of course, because I get a bad value. Exactly same working in ambiguity of radial velocity measurement. And why? Because you know, like example, in this example, if we have like carrier frequency 10 gigahertz, wavelength is 3 centimeters, PRI is 1 millisecond. So first blind speed is 15 meters per second, about 54 kilometers per hour. And what is mean this blind speed? Why occurs this blind speed? Because it's divided, it is important with, it is connected with PRI. So if I will compute speed of target, this, then if my target will move by speed doubled, tripled, and so on, for me same. It is depend on wavelength. Look, it will be, I can distinguish stationary target from targets moving at multiples of half of the wavelength during the repetition period. Look, it is 1 µ signal, 1 µ pulse second, and so on. It is different pulses. And this is moving target responses. If it will be shifted about half of length, I will get this result. This, always same. So it is mean he don't move. But if not will be about, it will be different value, you can see that it changes. It is very, very similar to ambiguity of in range, but it is in speed. So I can say that in speed, we call it this ambiguity, we call it blind speed. Why blind speed? Because all values we don't know that is right, so it is blind speed, and it is all multiplication of first radial speed are indistinguishable. So all this multiplication, and later I will show you how. And removing is in principle completely same like for range. Only I working with speed. And how I can improve and make higher blind speed, because of course I won't detect targets not at 15 meters per second. I want much higher, make higher PRF, and it is mean shorter PRI. And again we are back. It is opposite. Then I have one slide about measurement errors. Which kind? It will be quicker. So we have random, of course, effect of noise. Noise is everywhere. Effect of amplitude quantization. Of course, because I made AD conversion and quantization error, I think that you know it very well in electrical engineering what is quantization. Effect of sampling, because we are not sample exactly in same time, because there is also jittering. All this random effect I can relatively reduce by impact by averaging, longer CPI, better SNR. And what is CPI is coherent processing interval, because I always show you now, okay, we transmit one pulse, receive, one pulse, receive, one pulse, receive, but this causes pure resolution in Doppler. I need better, so I make integration through many and many pulses, not one pulse, but like through area of 100, 1000 pulses. Longer time of integration, it is improving. Okay, if until now is clear, I will continue to radar displays. It will be more interesting. You can see this is 4 base visualization of outputs: A scope, B scope, C scope, and PPI. If we need range only, we can use E scope. What is this? It is just amplitude of my response, and it is clear my target is there. This could be caused by noise or something, or it is weak target. Of course, it could be, but it is range, amplitude. B scope it is range and azimuth. So you need range and azimuth in one scan, because what is one scan? It is one rotation of antenna, and you are scanning this. After 6 seconds again I will scan same place, and so on and so on. So you can see in which azimuth. This gives you information about only about range, but I don't know angle. I don't know where is it. I know that it's in 50 kilometers far away from me, but I don't know where. This told me it is 50 kilometers in this azimuth. Then see scope, it is azimuth and elevation. So it is in azimuth and elevation, so I win exactly in 3D where is it. And PPI, it is range, and it is like this movement. Okay, and now we will go for animation. I prepare. You can see this is azimuth. What is mean this free? Static target, it is reflection from building, something what is not moving. And what is this? It is something what's moving, and it is far away from me, so amplitude decreasing because lower and lower energy. Is it clear? It is useful this for calibration or clutter studies or something like this. Then we have B scope. Again, free static target, and one is moving, azimuth and range, so you can see how it's move. By the way, this is not from real radar, it is just my simulation, but it looks very similar. This is C-scope, so azimuth and elevation, so you can see it just for one target. What do you think? What is disadvantages of this C-scope? Look at the axis. Okay, I know, azimuth, elevation, so it is clear.
Distance.
I don't know how far in this. Exactly, good point. And this is classic radar display. Probably you know it, this display. Exactly. Plan position indicator, PPI. Exactly. On other slides, I have examples from real radars from my friend that previously working in a radar company, so I will show you some real looking data. I think this you can see range, because of course position of radar is 0, 0, 0. It is there, so you can see. And what is this? It is your scan and every rotation. Of course, you can also make display of map, because it is like, is it possible to interconnect it? You can see, I don't know.
3D map.
Yeah. 3D, no, like 2D, I think. Like classic, if you have see map of airport, around airport, something like this. 3D not, because it is not 3D, so it is not like, how to say.
Scanning the center, and after that we have to create one line.
It is, yeah, it is like scan, so there is no elevation, it is just azimuth, there is no elevation. So
Connect two types of like elevation and this to make a 3D kind of into exact.
You will see, oh, okay, wait. Wait for this picture. It is from a real radar.
Yeah.
So you can see it is, what is this? White one, it is tracks. This individual detection in time. There is information I don't know exactly which one, of course, because I am not working with this. It could be about, I don't know, elevation, height. It could be ID of airplane. It could be anything. It is depends what you, of course, what radar knows about this, how to say. But this is real, like what sea radar operator. I don't know if in ATC radars in Guwahati, but will be something similar, if you understand me, because every radar has own visualization of targets. But this is classic PPI. This is presentation of B scope. This is PPI. This is PPI. This is B scope, and this is visualization of radar system. And why I put this screen? It is in Czech Republic, in Čáslav airport, and this is flat, you can see it. And there is hills. It is not looks like, but it is about 80, 100 meters, something like this. It is flat, 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 and go up like this. And this reflection is this reflection. Hill, it is not mountain, it is. But no, I joking. Yeah, it is like this. So, and this is in B scope, and exactly same information, it is in PPI. It is the same, just wrap it in another visualization. So you can see it is again distance, slant range, and phi is this azimuth. And this is position of your radar. And why do you think that there is some white space? Just guess.
Blind spots.
It is so-called dead zone of radar. Why? Because imagine, during transmission of your pulse, you can't receive. Plus some extended time. Why? Because reflection will be so strong that will destroy your receiver. So this is blind zoned. It is like, it is depends on many variables I will show you later. You can easily compute, but you understand me. So radar generally has blind zoned. And what is this maximum? It is maximum range of your radar. And there you can't saw it. So if we will have radar up to 450 kilometer, like this weather radar, this will be 450 kilometers. And blind zone will be, I don't know, 3 kilometers, something like this example. But I'm guessing because of course you need to put to equation and compute, but just imagine. So radar never see, never can detect anything what is in blind zone. Why? Because you're just not receiving information, because you are transmitting during this time, plus some amount of time that you will add to this after pulse. Because if there will be some big target really close to radar, the reflection will be so strong that you will destroy your receiver. And we call it blind or dead zone. Okay, I didn't watch time. I don't know. We are okay.
We have a tea break.
Tea break. Okay, so
lecture completed this or still is there?
no, there is 45 more slides. So should I continue or tea break?
If you have a short tea break, sir, then we can.
Okay, it is up to you, guy. And of course, on online people, so it is up to you. If you want break, we can make break.
Again,
If-
we can have means right now 3:45 at 4 o'clock again we can start.
Okay, okay.
Tutorial also is there for 1 hour.
Yeah. Okay, so it is up to you. For me, it's not important. I can deliver lecture in even in 2 hours in a row. No, I think that is good if we will make a break.
So we can have a strict tea break of 10-15 minutes.
Yeah. So we will come back at 4?
Yes.
Okay, perfect. So go for tea.